And we can begin. Good evening, everyone. Welcome to the September 2020 meeting of Berks County Amateur Astronomical Society. Always hit us up at berksastronomy.org or at our Facebook page, Berks Astronomy. Right before last month's second Thursday, we had an incident happen, and so that got my wheels turning, and so I reached out to the Reading Radio Club president, Chris Schlegel, and so we sort of threw this together in the past little bit, and now we're happy to hear more about how radio and astronomy are interdependent. So without further ado, thanks for joining us, Chris Schlegel.
Well, let me first by saying Elan and I have been talking about a presentation along this line for quite some time. So I know Elan, he started coming out to our meetings as an interest, and we've got to talking, and we have a lot of very similar interests. One of the things I had mentioned to him is I was looking at starting trying to assemble a radio telescope, and I piqued his interest apparently. So the parts are still here, not together due to an accident at work, but it's still on the books. I will get it done. I'll start out with my interest in radio astronomy. Basically started with amateur radio, SETI at home. I did a lot of number crunching for SETI at home over the years, and the movie Contact. That was, albeit sci-fi, but the nice imagery of the VLA, which you'll see later on again, it stuck to my heart. All right, so with that, I'm gonna start pulling up the presentation and getting everything situated. And you guys are gonna have to give me a couple minutes here because I actually have a split screen setup going.
That's okay. Are you prepared after this presentation for questions?
Yes.
Perfect. So if you're taking notes, people, we'll see what we can throw at Chris.
I will do my best to answer.
I think it's going great. You'll do. Thanks.
Nope, I want that pulled up yet. All right. So we kind of went through the intro bit already, and I'll start out with a little bit of technical background to help understand the remainder of it. I had mentioned to Elan, this is a really high-res scan of an old school, what I'll call a DC to daylight poster. And what I mean by DC to daylight is the electromagnetic spectrum encompasses everything from DC, which would be a flat waveform, to all the way up to X-rays, gamma rays, incredibly high frequency sine waves. So let me get the mouse pointer over here. Right here, in the visible light spectrum is what most of you are used to astronomy being. It's a very narrow range of the electromagnetic spectrum. Whereas we as amateur radio operators are used to looking down in this range. And it's a much wider range. And this is where radio telescopes become a thing. To kind of give you an idea, visible light, I'll refer to my notes here, runs basically from your red to your violet. Red is, when we refer to frequencies, we refer to them by not only their frequency, but also by the wavelength, the length of distance from one peak of the sine wave to the next peak. So red is roughly 405 terahertz, extremely high frequency. That's about 740 nanometers. So violet, which is at 790 terahertz, or about 380 nanometers. Now, Radio waves, on the other hand, much, much, much longer wavelength. Radio is typically defined as 3 hertz to 300 gigahertz, or 100,000 kilometers to 1 millimeter. So that incredibly long wavelength is one of the reasons why radio has some better abilities when it comes to astronomy over optics. I'll get into that a little bit later. What I do want to do is I do want to give a little bit of history, just some notable things in the beginning of radio astronomy. I'll get to these gentlemen in a minute. The 2 earliest radio astronomers as to who was first is kind of up for debate. One name that you're probably familiar with is Carl Jansky. In 1932, he was the first person to observe radiation from the Milky Way galaxy. He worked for Bell Labs, and they had some interference in the transatlantic communications that they were running, and Carl Jansky was tasked with finding that interference, and he actually was able to trace it down to radiation from the center of our galaxy. Not too long after that, a gentleman by the name of Grote Reber was an amateur radio operator. W9GFZ was his call sign. In 1937, he was the first person to build a radio telescope. It was a 9 meter parabolic dish in his backyard. The dish is actually currently held by the NRAO as a historical site. It was in Wheaton, Illinois. He actually surveyed the sky over several different frequencies and actually created the first radio frequency mappings of the sky around us. About 30 years later, Arno Penzias and Robert Wilson, the gentleman in the picture to the left, used this horn antenna in 1964 and 1965. Now, this horn antenna is the Holmdel horn antenna in New Jersey. What it was originally tasked to do was to bounce signals off of passive satellites. They were balloons that were illuminized. They were trying to bounce signals off those satellites and basically over the Atlantic. Later on, it was going to be used for the Telstar satellite, but it never got put into use for that particular reason. But during this usage for passive in the Telstar satellite, they had a lot of interference or background noise, and they couldn't figure out what it was. So these 2 gentlemen tried anything and everything to eliminate this background noise, to the point where they had to scare pigeons out of the horn antenna. They had to clean pigeon dung out of it, and they just couldn't get rid of it. So not too long around that same time period, they were talking about the Big Bang, and it was concluded that this background noise was actually cosmic microwave background noise from the Big Bang. And they won the Nobel Prize in 1978 for their research into this. So that was kind of really where radio astronomy started to take off. So why radio? I had said we would get back to that. Radio, with its much longer wavelengths, has the ability to penetrate the Earth's atmosphere a lot easier than a lot of the other frequencies that we would look at. Optical is one, and as you are well aware, optical has its limitations. Cloudy skies, fog, weather, even the atmosphere itself, even on a clear night, is still very attenuative of visible light. One of the reasons why the Hubble Space Telescope is such a big help to us as astronomers here on the surface. Radio, on the other hand, penetrates the Earth's atmosphere much easier. In fact, it's not just the Earth's atmosphere that it penetrates, but it also penetrates dust clouds, gas clouds, the distances of space a little bit easier and a little bit better than visible light. So that is another benefit. The other benefit of radio is dark body or dark matter objects out in space. A couple of the images I'll show you later on, you can really see the difference or what's going on in a particular part of the sky over and above what visible light shows. A couple of the examples I have for black body objects would be things like pulsars, magnetars, gas cloud emissions, and fast radio bursts. Things that we're beginning to just now, even with radio telescopes being in use for so long, beginning to understand. Fast radio bursts, essentially what they are is extremely quick emissions in the radio spectrum from things like pulsars. So how do they work? This actually should be fairly similar to what you're used to seeing with some of your telescopes, so optical telescopes. This particular image is of a Cassegrain radio telescope, very similar to the lens setup that you would see in a Cassegrain telescope, optical. Now, the big difference is the detection hardware. For an optical telescope, your detection hardware typically tends to be your eye. Here, we're using radio frequency receivers and filtration systems, and then using computers to digest that information and map it out. Find my cursor again. All right, so here are some examples of some radio telescopes. In the upper left, you have the 100-meter dish at Green Bank Observatory. That particular dish is the largest movable dish in the world. On the far top right, you have the new FAST dish in China. Like Arecibo, it uses the geography not only as a support structure, but also as a way to reduce terrestrial RF interference. FAST stands for 500-meter aperture spherical telescope. This particular telescope is expected to be 2 to 4 times more sensitive than Arecibo. In the lower left, you have the CHIME telescope. Now, the interesting thing about the CHIME telescope is there are no movable parts. It does not have to be aimed, and it is extremely wideband. This is a telescope that they're using right now to really dig into fast radio bursts. In the lower right, you have the VLA, the Very Large Array. Now, this particular telescope uses many smaller telescopes together in a phased array to increase the size and apparent aperture of the telescope. They essentially appear as one large telescope once all of the electronics are put into place to do the signal, can't think of the word, sorry. The signal digestion, I'll say. The image in the middle is a homemade horn antenna. This is one of those homebrew projects that you can do. You put it in your backyard, and one of the things that you can do with some other hardware to start radio astronomy in your own backyard. These particular antennas are made with the aluminized insulating sheet that you would put on your walls. The aluminum acts as a reflector in this case. It funnels the RF signal down into the back. If you look, there's the cursor. Down here in the back, they either use a box made out of the similar material, or the other way that they'll do that is with what they call a coffee can collector. They essentially use a coffee can with a small antenna positioned at a calculated distance inside the coffee can to receive your signal. So what exactly are they looking for? So at a very basic look at what a radio telescope sees are going to be similar images to what you see over here on the left side of the screen. Just a very simple spectral plot of a frequency. Sometimes they will also use strip charts to record movement over the telescope at a specific frequency. One of those would be the hydrogen line. Hydrogen, in its neutral state, will give off a radio emission once every 11 million years. Now, that doesn't sound like much, but given that hydrogen is the most abundant element in the universe, that little tiny peep shows up as a giant roar across the universe as you start taking into account all of this hydrogen. So hydrogen, that radio emission is around 1420 megahertz. And by using a strip chart and receiving that roar at 1420 megahertz, you can map out the hydrogen line emissions across the universe. So down here in the lower right-hand side, there's a website, HTTPS Radio Jove. Not all frequency, there are radio frequency emissions across the entire spectrum. Now, Radio Jove, let's see if I can pull up the website. Come on. There we go. So this particular site and the project is based off of the 24 megahertz emissions from Jupiter. It's in our own solar system, so it makes it very easy to observe and can be observed with nothing more than a very simple antenna in the backyard, literally a piece of wire. So on here, they have some sound clips. I'm just gonna play some sound clips real quick of what some of these might have. All right, was everybody able to hear that?
No, it froze for a moment for me.
Barb, I didn't hear your response.
You were frozen.
That was okay, so it's not gonna, it basically sounds like a bunch of very quick clicks. Now that doesn't sound like much, but if you go to the S-burst slowed down and listen to it, it's this very drawn out signal that changes frequency, audio frequency, very slowly, and it makes almost like music, and it's a very cool thing to see. So if you guys get a chance, check out this Radio Jove. If you Google search it, you should be able to bring this up. If you go on the main web page under sample audio, you can listen to some of those samples on your own. Believe it or not, there was actually a music artist that created a kind of like a techno-ish song out of these slowed down audio translations of what we hear in radio astronomy. All right, so we're going to get rid of Chrome here. Shove that off to the other side. So as amateur radio astronomers, it's becomes a little daunting to take this information from these strip charts or spectral plots and turn these into actual maps. And there is quite a bit of software out there to look at. And that's something that can be researched, if you're interested. But what places like Green Bank will do, or the other observatories, they actually have advanced computing software which will throw this all together based on the aperture size of the radio telescope, and it really puts things into perspective. In the top left here, you have a radio image in the 21 centimeter band of Jupiter versus what's visible, which is kind of interesting because Jupiter's just a ball, right? There's a lot more to Jupiter than just what we see. The top right is kind of an example of it's not necessarily RF spectrum, but how just changing the spectrum of the electromagnetic spectrum can change our perception of what we see. This is one of the, I don't remember exactly what they call the structure, but you can't see anything visible through it. But if you look at the infrared spectrum, we can see a whole lot behind it. The lower left, again, there's two separate sets of images here. Here you have three objects with visible. We really can't, we can see them, but we don't know how they're interacting. To the right of that, there it is. Here, using radio frequency, we can see how those three objects are interacting with each other. Down, I don't remember which galaxy this is, but that's the visible. And then on the right-hand side is an RF print from a radio telescope. You can see the jets coming off the center of the galaxy. So radio allows us to see not just that tiny little spectrum. Again, this is some of the benefits of using radio for astronomy. This lower right image is a radio emissions plot of the Milky Way galaxy. So we can really see some of that structure, or things that you would see above and beyond visible.
What did you say the upper right was?
Up here?
Yes.
That's just it's more or less an example picture. It's not necessarily radio frequency, but it's a comparison between visible light and infrared. And the reasoning for that image was to show how visible light is even though we can see very far with it, is still kind of limited in what we need to use to study the universe around us.
Right, but what is this? A Doppler cluster on a galaxy? What is it we're looking at?
I don't remember what it's called off the top of my head.
Is that the Coalsack?
Could be. There's a couple areas.
It's a dust cloud.
Yeah, it's an area in the night sky where we just visibly we can't see anything.
Okay, thank you.
I apologize. Yeah, you guys would probably be better to answer that than I could.
I'm not sure if that's dark nebula, if that's the technical term.
Yes.
See, you guys teach me something tonight too. All right, so what would you need to get started, or what are the hobbyist components to a radio telescope? So up here is SDR dongle. Now SDR stands for software defined radio. I'll try to stay away from the technical aspect of that. But essentially what it does is it takes a huge wideband spectrum of RF and it turns it into a digital signal, and the computer does all the hard work. Now to kind of give you an idea for reference, next to my face, my nose, whatever, this is one of those SDR dongles. They cost about 25 bucks. And they have an effective bandwidth of about 2.4 megahertz. Not real wide, but still usable. And they come in all shapes, flavors, and sizes. This is about the cheapest one at about 25 bucks. For comparison, down below, you have a commercial professional version from Edis Research. These are capable of about 50 megahertz worth of spectrum visible at one time. They go for several $1,000s a pop. Now, again, this is still nothing compared to what you would find in a radio telescope. Hardware that they have is incredible. So going from your receiver, you would also need amplification and filtration to help keep that signal clean and pertinent to what you're trying to observe. Now, this is a LNA, low noise amplifier. This is a very popular one built by a hobbyist in Croatia. He's an amateur radio operator. They sell for $30 or $40 a pop. Right now, he's not producing any due to the COVID-19. However, you can find other LNAs online. RTLSDR.com makes an LNA that is very comparable. I did not include any images of any kind of filtration in here, only because there is a significant amount of different types of filtration. Everything from cavity filters, strip line filters, to simple RLC filters. Down in the middle, this was kind of a joke. The computer for digesting the information. Now, this is an actual rack out of a radio telescope. As you can see, they have a significant amount of computing hardware, and this is still relatively small. Kind of give you an idea, I mentioned the computer systems at the VLA. They are near supercomputer in strength when they try to reassemble the signals from all of the individual telescopes. Lastly, you would need an antenna. Now, I had mentioned the radio Jove being around the 24 megahertz. This image in the upper right, you see these poles. It's not very easy to see, but there's a wire ran from one pole to the other pole. And there's actually two of them here. It's a phased dipole. That is literally the only antenna that they're using to receive signals from Jupiter for observations. In comparison, down here at the bottom right, an old C-band satellite dish. It is very popular for amateur radio astronomers to scavenge old C-band satellite dishes and use them. Now, take notice, this doesn't have the nose piece on it, the collector. The reason for that is most of the time you have to build your own. And again, the most common one is that coffee can collector. You learn a little bit about parabolic dish design, where it needs to be placed, dish illumination, spillover, very similar terms to what you might see in designing a telescope from scratch with the mirrors. And once you get past that coffee can collector, there's all kinds of receivers that you can put in there. To give a real quick example though, what a lot of people will do is they'll mount the receiver and the filtration and amplifiers all on that collector for the dish. That way there's very little loss between the collector and what's going out to the computer. Before I get into that, I did have some information pulled up on frequency, which I'll kind of spout off real quick. So to kind of give you guys some idea on what frequencies you would be looking at. Now, a lot of the frequencies of interest for radio astronomy are actually protected. 73 megahertz, 150 megahertz, 406 megahertz segments. Those are very popular frequencies for pulsar detection. The 1420 megahertz I had mentioned for hydrogen line, and then it goes up from there. To kind of give you an idea, I was surprised earlier in just reading about the 100-meter dish at Green Bank. That particular dish is capable of receiving signals from 100 megahertz to 116 gigahertz. So extremely wideband capability. So I didn't want to leave my amateur radio out of all of this, and hence the title of the presentation, where it was radio and astronomy. I see you chuckling, Elan. So I wanted to mention how radio here on terrestrial Earth is just as important as it is out in space. So one of the things in amateur radio that we really pay attention to is the solar cycle. The reason for this is the sun's play with our own atmosphere affects the way radio propagates here on Earth. So solar cycles run an 11-year cycle. Kind of have this imagery on the left-hand side and the chart for the past couple of cycles on the right-hand side. Now, the past cycle that we were in, cycle 24, was actually relatively weak. We almost had a double peak to it. And there was a bit of a delay between the end of cycle 24 here and the beginning of cycle 25. So there was a lot of us who were starting to get worried that we were going to start entering another minimum. So how does the sun affect radio wave propagation here on Earth? Well, the sun's radiation ionizes our ionosphere, and it actually acts like a mirror for radio waves dependent upon how active the sun is. So the image on the left kind of shows that a little bit, and it shows the layers of the ionosphere that we're paying attention to: the D, the E, the F1, and F2. The F1 and F2 layers are the ones that are the most important for us as amateur radio operators. The E and the ES, we pay attention to that a little bit less. You start seeing tropospheric ducting. Kind of give you an idea what that is based on temperature inversions, some minor activity in the ionosphere. We can get very far propagation. There's a mode in amateur radio called APRS. Typical propagation might be a few hundred miles. Over the last couple of days, we've had some very strong tropospheric ducting and ES. I've been receiving packets from as far away as 700 miles in Nova Scotia. So kind of an example. Now, it's not just during the day. We also see this at night too, due to the leftover remnants of being energized by the sun. At night, this image on the right shows you how the F layer combines to a single layer at night, and during the day splits to the F1 and F2. And that's again due to that ionization from the sun. Oop. All right. So Barb and Elan, you might remember this from our last discussion. I had talked about the solar flare and my personal experience with it. Actually, I'm going to take a step back. Elan, you had asked last month about some of the things that we pay attention to and what they mean. The SFI number, the solar flux index, it's the received energy from the sun at 10.7 centimeter band. It's up in the gigahertz range. That number is turned into a factor number. The higher the factor number, the more interested we are, because it means that the sun is capable of ionizing our atmosphere that much more. The K value is a calculated factor that is measured every 3 hours. And again, the lower the number there shows less noise and interference to RF here on Earth. The A factor is a 24 average of the K index values. Same thing again. The lower the number, the less interference that we have here on Earth from atmospherics. And then we also pay attention to the daily sunspot number. More sunspots equal more ionization of our atmosphere, better for us in our propagation. Now, to kind of give you an idea, over the last year and a half, 2 years, our major bands, major frequencies that we use in amateur radio have been the 40 meter and 80 meter bands, 7 megahertz and 3 megahertz. During years in the peak of the sunspot cycles, we can use frequencies to talk as far away as, well, I'll get back to that in a minute. We can use higher frequencies. 20 meter band at the 14 megahertz, the 10 meter band in the 27 to 28 megahertz range. They have been used to make contacts all over the world. My farthest contact going east is in Saudi Arabia with nothing more than a piece of wire back in 2014, to give you an idea. So very, very far contacts. I have not personally had the experience of a very good solar cycle. However, some of the hams in our club have, and it's been very interesting to hear them talk about their own echo, where propagation was so good that their signal bounced off the ionosphere back to Earth and back up again so many times, they could hear their own RF signal coming back from around the other side of the planet. Think about that for a minute. All right. So back to the solar radiation and the solar flares. One of the other things that we pay attention to are solar flares and coronal mass ejections. They both can cause some very, very heavy RF disturbance here on terrestrial Earth. Coronal mass ejections will cause long-term minor magnetic changes in our atmosphere, which will cause higher than normal what we call the noise floor, and can cause loss of signal sensitivity. Solar flares, on the other hand, they can completely blanket the RF spectrum and make everything so noisy that we can't hear anything at all. So a personal experience with this, and it was very eerie having it happen to me. Back in 2017, we had the two highest solar flares, the two strongest solar flares in the last solar cycle. So this particular one that I have an ionosonde for, and what an ionosonde is a RF transmission that is shot straight up into the sky and bounced back to Earth across a spectrum of RF frequency. And they measure which frequencies bounce back to Earth and which penetrate the ionosphere and continue going on. So trying to not to get too technical into this, this line here shows the frequencies up to about here that were being reflected back down into Earth. Maximum usable frequency over here, that's the highest frequency that we can use before it starts to penetrate the ionosphere and does not bounce back to Earth. So a couple days prior to this was the strongest of cycle 24, as you see above, was an X9.3. Now that particular solar flare was so strong that it actually wiped out the GPS system for about an hour and a half. Not even military GPS satellites were capable of operating at that time. Now the ionosonde that you see here was 4 days later on September 10th. I was on the radio, I was talking to somebody over in Europe, and we were trying to complete our contact, and as you can see from the time, and this one was 15:46 and over here 15:52, literally 4 minutes later, he was gone. I could hear him clear as day before, and then all of a sudden he was gone. I actually got up from the radio station and went looking at my antenna to make sure everything was still hooked up and something didn't happen, because I didn't hear anybody. There was nobody on the band at all. And it kind of hit me, well, let me check the ionosonde, and here you can see we went from having some kind of bounce to completely wiped clean. So that was a personal experience with it. Barb, you'll remember we talked about the Carrington event last month. That was arguably one of the strongest solar flares in recorded history. Several times the magnitude of what occurred here in 2017. The story goes that the solar flare actually induced so much current into the telegraph lines at the time that Morse code operators' keys were arcing on their own and they were getting shocked. A solar flare of that intensity nowadays would cause widespread destruction across our power grid, our communications, everything. Everything we have nowadays is so sensitive to that kind of energy.
When was this?
Go ahead.
What year was this?
This was in 1859.
Okay, thank you.
I apologize. I should have thrown that out there. So looking to the future on this kind of thing, not only do we really want to keep an eye on the RF spectrum, not only for usage in radio astronomy or amateur radio, but in our own solar system. Did some research into that Carrington event, Barb, and you might find this interesting too. There were several solar flares in quick succession, and they think it was so strong because the first solar flare paved the way for the second, which occurred, I believe it was a day or two later, and it actually allowed the solar flare to hit Earth significantly faster, which looking at, the ones of 2017 kind of got a little interesting because they were only 4 days apart. So we're due. Yeah, could be interesting. All right. I know I kind of flew through that, and I apologize. I'm kind of nervous on this one. But any questions?
I have 3 questions.
Shoot.
Okay. And some of them may be in your lane of expertise, some may not. Just let me know either way.
Will do.
Okay, the first question is, let me just get all the questions out so you have them all to work with. The first is, what sorts of conferences are there in websites where I could learn more? Second question is, with the climate change, and more specifically with the increases in carbon dioxide and methane, are those substances irrelevant to the ability for radio waves of across the gigahertz range to propagate and up to terahertz range? And the third question is, when for certain gigahertz, I have an interest in microwave and millimeter wave. That's why I'm asking these questions. For the wavelengths that are absorbed by water or by oxygen, I don't remember. It's 100 plus gigahertz. I don't remember exactly what the number is. I'm curious why those particular frequencies are so absorbed by water or by oxygen, because the wavelengths are nowhere near the bond lengths involved. So if you could shed any light on that. Like I said, some of these may be in your lane, some may not. Just whatever you can answer would be appreciated.
Okay, so as when it comes for websites, there's a plethora of them online. Everything from Canadian open source radio telescopes to can't think of the name. Give me 1 second. I literally have a huge bookmark file full of stuff. I'll show you real quick.
Yeah.
If I can get everything in place. Actually, I don't have it shared, so I can't. But yes, there's a plethora of things that you can find. The NRAO has some stuff that you can find. NASA has stuff. When it comes to the radio side of things, there's a lot of stuff out there for SDR right now that you can use. In fact, there's a gentleman who teaches new radio over YouTube videos. What new radio is it, since these software-defined radios don't really have a front end to them, it's just the receiver. The computer acts as the front end digitally. New radio, basically, you can program it to do whatever you want. You can turn it into an AM receiver, a microwave receiver. It's a very complex, very powerful program that is used by amateurs and commercial entities alike. When it comes to your second question, I apologize. Can you repeat it?
The increase in CH4 and CO2 into the atmosphere, are those irrelevant as far as being able to do radio astronomy?
Yes and no. Immediately when it comes to a molecular level, yes, it's irrelevant. Radio waves would penetrate them very easily. However, those particular gases increase tropospheric ducting, heating differences, thermal differences in our atmosphere. So at frequencies in VHF and UHF, yes, it would definitely affect the way that radio astronomy is able to operate. Now, one of the things that you will find with things like that is most radio telescopes are built in places that are either regulated or sheltered from RF. For instance, the NRAO Green Bank is in the National Radio Quiet Zone. In fact, in Green Bank alone, they're not allowed any wireless transmission, no cell phones, no Wi-Fi, nothing. Everything has to be hardlined or very, very, very weak that it doesn't overload the telescope. So it's kind of a yes and no answer to that one. And I believe your third question came down to wavelength versus water or the gases that are being observed, correct?
Water and oxygen have, as you well know, I'm sure you well know, are very highly absorptive of radio waves at certain frequencies. And I was just curious, those frequencies are in the centimeter range, I believe. And I'm just wondering how that's possible that they can be absorbed so readily by water and oxygen if their wavelengths are nothing near the the molecular bond lengths of the molecules involved.
So when it comes to oxygen, I really can't answer, but when it comes to water, that I can. Now, water molecules are absorbed at the frequency of roughly around 2.4 gigahertz very, very well. As an example, your microwave that you use to heat up food is nothing more than an extremely high-powered radio transmitter. Now, the reason why they transmit at 2.4 gigahertz is because water is absorptive, yeah, I can't say the word, of that radio frequency is excited, heated up, and heats your food from the inside via exciting that water. Again, it's the same reason why Wi-Fi was originally based around the 2.4 gigahertz spectrum, was to kind of cut down on the distance that it would transmit. So the way that happens is water molecules versus when they kind of coalesce into droplets are about the same size as the yeah. I don't have a full answer on that. I don't have an exact explanation for you, but yes, that particular frequency is an example. Let's see. Yeah, I really don't have much more for you on that.
Okay, thanks. By the way, I appreciate your answers, and in particular the answer to the second question when you talked about the quiet zones actually answered a fourth question I was going to ask you, and that's all I'm done. Which was, do we have to worry about the equivalent of light pollution for radio astronomy? And effectively, I believe the answer is yes.
I didn't quite catch that. Could you repeat it?
My question was going to be, which you answered, is do we have to worry about the equivalent of light pollution for radio astronomy? And apparently, given you said that certain radio astronomy telescopes have to be in quiet zones, apparently the answer is yes.
Absolutely. The radio spectrum, just like light, is getting extremely polluted. We as amateur radio operators have to worry about that ourselves, as do just about anything on the spectrum. So yes, radio telescopes are highly protected, especially here in the United States, and that is a big reason for it.
So they're basically in areas that are closed off from other radio emissions, I take it.
Correct, and that's kind of I'll lead some personal experience into that. As many of the ham radio operators in the area can tell you, I live in a geographical bowl here in Blandon, Pennsylvania, which actually kind of leads me to the point where radio astronomy in my backyard would actually kind of be a good thing, because a lot of the RF interference in the area is blocked via the geographics of my area.
Okay, thanks very much. Appreciate it.
You're welcome.
Interesting talk. Thank you.
Any other questions? I hope I hope I didn't fly through anything too terribly fast, and I hope I laid a very basic structure down for you as to what radio astronomy is and how radio affects us here on Earth.
I enjoyed it. Thank you.
Thank you.
Very interesting.
We had a question in our chat. Would you be able to send the incredibly informative looking electromagnetic infographic you used as the first slide of your presentation? Also, thanks for your presentation. It's very interesting. When you say contact, do you mean you can communicate with other radio telescope users with sound? I.e., you're essentially able to have a telephone call with someone else's radio telescope? And that's from Andrew Moses Yanet.
So
Great.
yes, I can send you the infographic. I just need an email address to send it. It is very large. So
it's a big graphic. I was pretty impressed by it. And if you could, even post it to the Facebook, we'll share it as we can.
I'll see if I can do that. That's a good idea. I believe the original image was several hundred megabytes in size, so I won't be able to put the original image up.
Okay, fair enough.
When I say contact, in amateur radio, it's very much like talking over the phone, except it's not bidirectional. You can't both talk at the same time unless you're on two separate frequencies simultaneously. It's what we call half duplex. So a contact is nothing more than a couple of guys getting together to rag chew, to talk to each other, what we call rag chew on the air, and or actually exchanging information for a logged contact. In amateur radio, we try to log all of our contacts, not only for awards and other things, but also to keep a record of who we've talked to, what our station is capable of, how far we can reach out. As I mentioned before, my farthest contact going east was Saudi Arabia. My farthest contact going west is actually the far side of Australia. And those are all logged contacts that I can use not only for my own purposes, but to get awards. So yeah, no, trying to communicate with, you can talk to each other using parabolic dishes and radio telescopes, but those are more along the lines of something like a microwave dish. And if you look up on top of any major mountain in the area, you'll see these big drum-looking things on the side of a tower. Those are actually microwave dishes, parabolic dishes that have a cover on them to protect them. Those are microwave links, high speed, high data rate, high voice, high quality links between towers. In fact, Elan, you're probably familiar with WEEU's microwave link between the tower site and your offices. So with a radio telescope, if you look at SETI at home, the idea is we could have a voice contact with somebody not in our solar system, since most of those are pointed at the sky. Andrew, I will try to email that to you. Thank you for giving me your email address. Google Drive might be the way to go. I'll see what I can do. Any other questions?
I had a few. I should have written them down. Question about the wavelength sizes. So you said that the radio spectrum goes all the way down to, did you say 3 kilometers or
3 hertz? So 3 cycles a second. It would actually be in the audible spectrum if you turned it into an audio sound. That is roughly around 100,000 kilometers. Now, generally we don't use communications that far down. About the lowest that amateur radio goes would be around the 30 kilohertz range in the VLF, very low frequency. Now, to kind of give you an idea of what that is used for, is the United States military uses that to communicate with submarines around the world, because those frequencies will penetrate the earth.
Wow.
And those are super long frequencies. I believe our lowest frequency is 2,200 meters for amateur radio for our licensing through the FCC.
2,200 meters. And so was Arecibo, oh my goodness. Is Arecibo, what is it, 100 meters?
Arecibo was, I think it's 1,000 feet across. So you're looking somewhere around the odds of about 330 meters. Maybe a little less, probably about 300 meters. And that's where the FAST telescope in China has its edge, is it's almost double the size.
So my curiosity was that you can receive radio signals in shorter dishes than their wavelength.
Yes and no. Generally, when it comes to parabolic dish design, the dish reflector part of the dish needs to be at least the size of the wavelength of the signal you're trying to receive. So like the 100-meter dish at Green Bank, anything from 100 megahertz to 116 gigahertz. At 100 megahertz, your wavelength is roughly 3 meters, maybe wow. 3.5 meters. So that dish is still significantly larger than the wavelength that it's trying to receive. Arecibo, you recall some of the frequencies they were talking about before, they were pretty much in the microwave range, somewhere down as low as VHF. But again, you generally want a dish that's at least the size of the wavelength that you're trying to collect.
All right. I have a dish that maybe we'll take a look at. We'll see what we can do.
Well, to kind of give you an idea, a lot of experiments for schools and stuff have been done with just the simple dish satellites, the satellite TV dishes from Dish or DirecTV. Now they're not very big and they don't give you a whole lot, but they can be used to do things like solar radiation observations. Basically, you would use a receiving setup or even nothing more than just one of the satellite locating devices that beep. They're roughly in the same frequency as that. So as you pass that telescope over I'll call it a telescope at that point, over the face of the sun, you should see an increase in the amount of noise that's received by that dish. Larger dishes, I mean, the 1.2 meter dish that I have, again, it's even for mapping hydrogen line, it's not really that great because the beam width of the antenna is still significant. I think the calculated beam width on that 1.2 meter dish is like 15 degrees. It's a real wide, swath of the sky that I would be observing. It wouldn't give me a very high-res image of the sky, but it would be enough to at least experiment and see where the hydrogen is most concentrated in the night sky. And that's where, again, the larger the dish or the larger the apparent size in the idea of the VLA gives you that beam width that is very, very tiny. I believe the fast dish was something like 0.1 degrees of the night sky is what it's capable of. I might be wrong. But what they do is that extreme definition then of the night sky allows them to create those very high-res images of RF across the night sky or the universe. Make sense?
Yeah, very cool. Thank you.
Other questions?
Can't think of any. But enjoyed your program.
Yeah.
Thank you.
Are phased arrays used to point the direction that our antennas want to look at for this type of work or not?
Angelo, I'm sorry, you were kind of getting a little distorted. Can you repeat that?
Well, for this type of radio astronomy, does technology use phased arrays, basically sets of antennas that you can use to focus the direction that you want to quote unquote listen to?
Yes, correct. It's constructive and deconstructive interference, essentially. Just like you would see waves in a pond, where the reflected wave hits the fundamental wave, and if they hit just right, they'll build themselves up and strengthen the signal, is essentially the same thing that they're doing with the VLA. The computational systems at the VLA, what they have to do is they have to modify the phase of the signal coming in from each one of the telescopes to make them constructive so that they all build themselves up. That's where they get that amplification from. You might have this real tiny little signal from each telescope, but by digitally and or through hardware changing the phase of that sine wave and making them constructive, that's where you get that amplification. Does that answer your question?
Yeah, well, given that they do that for the VLA, do they also do that to, let's say, point the direction that the VLA wants to look at, like at this galaxy versus that galaxy?
No, my understanding of the VLA is they actually point the individual dishes together they actually operate as a single unit. So if they pick a point in the sky they want to look at, all of the satellite dishes will move based on the control system together, like Elan's showing, to a very tiny fraction of a degree difference, just to make sure that they're all pointed at the same place. Is that what you were asking?
Yeah, that's what I was asking about. Thank you.
Okay. One of the things I forgot to mention, and Angelo, this kind of goes on what you were asking, they have started using high-speed internet to use various radio telescopes across the entire Earth as a phased array. And that is something that we are really starting to dive into and get some really cool observations from.
Well, that sounds pretty neat. That sounds somewhat analogous to some ideas of using across the Earth or even further than that for having sensors to measure very larger resolution gravitational wave astronomy. Not the same thing, but analogous.
Yes, very much so. It is only with the fact that our internet and our ability to not only modify those signals, but recombine them at the appropriate time to within very tiny fractions of an error that is allowing us to do that.
Does the influx of or the planned increase of large numbers of satellites, is that going to be an issue for this type of work?
Yes, and where that becomes an issue is a lot of those are made out of metal and they do reflect signals back. Now, I don't know how many of you have seen some of the imagery of the number of satellites or space junk that's out there to begin with. It's phenomenal. Yes, there's some concern in the scientific community about these massive massive satellite constellations that they're trying to put up. So not only is it becoming an issue for visible astronomy, but it's also becoming an issue for RF and radio astronomy alike.
Thank you.
You're welcome. All right. Anything else?
Any other questions?
No?
All right.
I don't know enough about the subject to ask a question.
Well, hopefully a little more than an hour ago.
Yeah, yes.
Yeah. So
right.
there's actually a night sky network tonight. They're going to be talking about observing the moon, a little bit more about the moon tonight, and that's coming up in about 15 minutes. So I wanted to give you a little bit of time and a heads up about that. Mid-September, Rocket Lab is projected to do something at their launch pad at Mars facility, the Mid-Atlantic Regional Spaceport. So more on that later. More updates about a star party, and second and fourth Thursdays, 7:30, Berks Astronomy hangouts on fourth Thursdays if it's not the recap meeting. Anything anyone would like to add?
Well, I'd like to ask Angelo a question.
Yeah.
Yeah. Do you want to order calendars this year?
Yes, let me email you.
Okay. I'll be placing the order in another week or two.
All right, thanks. And hopefully we won't have any solar flares while I email you.
All right. Anything to add? Any other space news people are excited about, or off to Night Sky Network?
Well, they'll be launching a Antares rocket from Wallops at the end of September.
Oh,
September 29th. And it's at nighttime launch, so we should be able to see it pretty good.
awesome. Yeah, I'm real excited about the launches. I'm glad this didn't turn into an hour-long rage at some satellite constellations out there. But yeah, more on that later. We'll see what else we can do as far as, well, the satellite thing. Chris, I don't I don't think you've contacted the International Space Station, right?
Not recently, but I have already.
Okay.
Well, that's cool.
Yeah, I haven't spoke with any of the astronauts. Now that happens very rarely anymore due to their schedule.
Right.
However, there are several pieces of amateur radio gear on there. Earlier I mentioned APRS, automatic position reporting system. It's basically a packetized data transmission. We can send messages, location information. There is a digipeater. It's essentially a repeater that's made to transmit these retransmit these radio packets. And I've already used that to make contacts back here on Earth by bouncing APRS packets off the digipeater on the ISS.
Very cool. I suppose the coastal Australia and Saudi Arabia are a bit further than the 250 or so miles to the space station.
Yes. You had mentioned about the ISS. One of the things I did forget to mention might be of interest. There is actually a subset of amateur radio. We actually have our own satellites in space as well. Small microsats that have RF equipment on them that we use like repeaters here on Earth, where we can make contacts through the satellite. So again, that subset of amateur radio kind of involves the astrophysics part of astronomy, where we have to learn how to use the telemetry, the ephemeris, to make predictions on the satellite passes and that kind of thing. So I've made several satellite contacts in that way as well.
Very cool. All
And I'll
right.
try to be in touch with Dave Brown tomorrow about the Skywatch for tomorrow night.
Okay.
Try to get something out if we decide to if we can postpone it or whatever.
Yeah, I don't think I want to test how much rainwater I can collect in my telescope.
I'm saying
I
this.
know, got hammered leaving Dave's last time.
If you're trying to reschedule it for a good time, I saw on the weather forecast today, next week's supposed to be beautiful.
Monday, Tuesday,
Yes.
Wednesday. I'd like to put something together. We'll see what we can do. But hopefully, we'll see. I might be out somewhere with my telescope anyway. So.
Given our weather, we should transition from visible light to radio astronomy with dishes and umbrellas.
Elon, when I finally get that backyard radio telescope up and running, I will have to either take video or make it portable enough to bring it out and try to bring it to one of your actual in-person meetings if able to.
If
That'd
you're
be
able,
cool.
yeah, that would be super cool. Take pictures as you build it, if you like, because I know there's plenty of those just rusting away, and if they can be repurposed for astronomy, that sounds really cool to me. So I'm definitely interested in following that story, and I think there's a 2-meter dish around. So more on that later.
The funny thing is a lot of people will pay you to take them.
Interesting.
That's something I've been looking at for the future, is trying to see where some of the larger C-band dishes are still up and keeping that in the back of my head. Now I just got to con the wife into letting me do it. She's not too happy about the big sticks in the backyard to begin with, the big antennas. So
Setting up. No.
I don't know how she would feel about a 10 or 12-foot dish in the backyard.
More infrastructure for the roof, right? All right. Well, on that note, more later. Definitely good things to look forward to as things go on, but I'm glad we're able to meet and connect online with this sort of thing. Any questions, berksastronomy@gmail.com or at our Facebook page, Berks Astronomy. Also, hit up Reading Radio Club's page on Facebook, as well as, do you have a website?
We do. If you Google search it, it pops up right at the top of the list.
Reading Radio Club. All right. And then this will make it to the interwebs, and we will see each other probably there soon. So thanks everyone for joining. We had a lot of great presentations and thank yous in the comments, and I can't thank you enough for joining us. Thanks, Chris, for putting this together, just so we can learn a little more about the bridge between radio and astronomy. So thanks again. Cheers to all, and clear dark skies.
Hopefully.
Hopefully. All right, take good care, everyone. Good night.
Good night.
Good night.
Night.